all the information is in this matrix, but you can think of this matrix as being embedded in a bigger matrix, which is 16 by 16, and then contains all vectors instead of all pairs of vectors which are parallel. And if you have that, then you have vectors which are not equal but are orthogonal to each other. No. Sure, yeah. But, okay. Forget what I said. But yeah, so the information is all contained in this. So for example, what do I mean information is all contained in this? Well, if you want to know what instead of the first vector, you want to know what the 9th vector would give you if you multiply it by the first vector, then it's going to be this thing, okay, the thing that would go here, and it has to be this. Otherwise, this orthogonality predicate wouldn't be well defined on pairs of parallel vectors. But it is well defined because you just multiply by -1. Okay, so the basic idea of the algorithm is you pick a pair. Okay, so you have to traverse all pairs of vectors. So by vectors I mean pairs of parallel vectors. So you need to traverse all pairs of parallel vectors. Okay, but if you just think of the first vector in the pair as just a vector, then you're fine. You just say you have to traverse all pairs of vectors. By vectors I mean just the first 8 one, and for each such pair you go through all the columns. Okay, you start with a footprint which corresponds to the empty set, so the set of possibilities for the product of two coordinates is just empty. And then if you hit a point where you have constraints that are mutually satisfied by in the two corresponding rows, then you look at the corresponding vector which satisfies both constraints, and then you look at the footprint and you combine this footprint by union with the total footprint. So you start with empty footprint, which is null, and then if you see a vector which satisfies all the constraints, you combine the footprint. And so here, for example, you would start with null, and then you would combine the footprint for this vector, and you would combine the footprint for this vector. But if you start in these two columns, then you would not do that, because you would never reach a point where there's mutual satisfaction of two constraints. In that case, you would end up with the footprint being null. Okay. But if you end up with a footprint being null, it's an automatic contradiction. It simply means the set of possibilities is empty. So again, read the relevant part of the thesis. If it's not null, then simply print all the whole footprint, the total footprint. And basically this is what it gives. This is a proof. Based on the theorem, we have like the sort of enabling theorem of this algorithm. This output, the fact that the algorithm outputs this, is a proof of the thing. You have to read the thesis, of course. So if you look at the first pair of vectors, so vector 1, vector 0 and 1, and you reach a contradiction. 0, 2, you reach a contradiction. 0, 3, for the first pair of coordinates, you get just a singleton -1 as the set of possibilities. For the 4 middle ones, you get the full set containing +1 and -1. For the last, you get -1, which means it's still a contradiction, because again, the fact that you have -1 and not 0 means that there's a perfect correlation between all the free rows in these two, in the columns corresponding to the pair of coordinates that this is. So the first two coordinates, all the free rows are perfectly correlated. The product is always -1, and so if you have and this is going to sound completely crazy if you haven't read, but if you have, this is going to limit the amount of free rows, because we know that because it's the beginning point and the ending point of the flipping pattern are both Hadamard matrices, we know that the total product of these two columns has to be 0. So we have a sum of these piecewise, pointwise products, which is going to be 0. But all the free rows give you -1, and so you can't have all of them being free rows, because then you would never get 0. So the maximum amount of free rows has to be the dimension over 2. And we know that each row that has at least one flip has at least 2 flips. So that you have at least number of flips equal or bigger than the dimension. And because of that, so this is the only thing we wanted, basically. Or you could say we assume that there were less flips than the number of the dimension, and then this would lead to a contradiction. Okay, and you can see for all the pairs, this is what happens. You could have computed this by hand if you somehow don't like the idea of letting the computer do the proof for you. You could have computed all of these things by hand. You would get the same thing. And a few interesting things to notice is that you always have 2 pairs of coordinates, which sort of lead to a contradiction. You never have 3 pairs or 4 pairs or 5 pairs or 6 pairs. You only have 2. You either have 2 or you have a contradiction. And yeah, so after this point, we've gone through all the possible, actually, yeah. So the reason it's 7 instead of 8 is because we start at 0, remember. So all possible pairs, and we either get a direct contradiction or an indirect contradiction. So you can verify this by hand if you're in doubt. And so this is just a little test to show you what the enumeration looks like. Alright, so now that I've gone through the whole thing, hopefully it was helpful. If it's the first time you've seen anything like that, then you can go through yourself and sort of question the decisions I made, because then in the naive implementation there's no need for a matrix. So why did I use a matrix? Okay, why did I store the orthogonality of both of the 2 rows? Well, you can just if there had been like lots of rows and lots of columns, then there would be many more pairs of rows than rows, right? And so if you compute the orthogonality matrix like this, you save the work of the naive thing. You know, and you also get a visual representation. You know, at this point, if you write the corresponding vectors here, most people would probably be comfortable to just go through manually and then check everything. So it's, you get a nice visual representation of the work you're doing. Yeah, so again, it doesn't matter, but the few things that will affect performance is you know, keeping everything small in memory, and while at the same time, I should say it's not completely true, but keeping everything small and uniform. Yeah. So one of the things that we could have done to improve performance would have been to compute the footprints for each column only once, but again, for this case where we only have what dimension is 4, and we're looking only at pairs of vectors for our constraints, it's pretty easy what's going on. But you see that the same kind of framework would work if you wanted to, instead of looking at dimension 4, you wanted dimension 6, then it's likely that you don't just need pairs of vectors, you need like triplets of vectors or something like that. And you can see this very easily. So again, play with this, make sure you understand everything that's going on here, and yeah, thanks for watching. Hopefully this has been helpful.